probably muted at the moment.
No, I just muted it. Good morning, everybody. I'm going to give 2 revision lectures. This morning's lecture will be on normal modes, and tomorrow's lecture will be on dispersion and waves. So this morning's subject is somewhat easier because it's all essentially one mathematical problem, which I'll just lay out very briefly. So the components of the problems are the equations of motion, the matrix formulation, and you expect the matrix formulation to look something like m x double dot equals minus k x, where m and k are matrices. M might be a diagonal matrix. The normal mode solution, which is x equals f of tc. So all the components of x vary in the same way with t. And if you substitute that in, you get mc f double dot equals minus kc f. And as long as f isn't everywhere 0, which represents a kind of failure of this mode of solution, you can divide by it. And what we now see is, and I'll take the minus sign over the other side as well, we have k, matrix K multiplied by vector C is that lot multiplied by C. This side is time independent, so this side had better be time independent. So that divided by that had better be some time independent constant, which you might want to call minus omega squared. The reason for giving it a minus sign is because we expect oscillatory solutions, not exponential solutions. And so now we have Kc equals kappa. No, I said I wasn't going to do that, wasn't I? Kc equals lambda c, where lambda is m omega squared. That is the eigenvalue equation. That has eigenvalues and eigenvectors, and so I don't propose to normalize any eigenvectors at any point, and so we end up with a solution which would be some arbitrary linear combination of those. So we'd have x is the f double dot over f equation. I mean, the other equation is d2f by t squared is minus omega squared f, which has solutions cos omega t and sine omega t. And so we can superpose all that lot with arbitrary constants to get a completely general solution. A is a1 cos omega 1 t times c1 plus a2 cos omega 2 t times second eigenvector plus b1 sine omega 1 t times c1 plus b2 sine omega 2 t times ct. And then the only problem is fitting some initial conditions. And so suppose that x of 0 is given and dx by dt at 0 is v some velocity vector. The way I've split out coses and sines means that the initial value is contributed by these cosine terms because the sines are 0. The initial rate of change is given by the sine terms because the cosines are 0. And so if you substitute that, you get x of 0 is a1 c1 plus a2 c2. And if you differentiate and substitute, you get v is b2 omega 1 c1 plus b2 omega 2 c2. And so that's the initial value problem, and it's relatively easily solved. I mean, if the eigenvectors have some special structure, then of course that might simplify things. But in complete generality, what you do is you use the orthogonality property of the eigenvectors, which looks like this. M C1 C2 transpose is now, I've assumed here that M was a constant, which, in other words, a diagonal matrix. If M is not a diagonal matrix, then it appears here, and the eigenvalue is omega squared. That's the only change. Let's go with M being a constant for the moment. In that case, C1 transpose C2 is 0. That's the orthogonality property. More generally, C1 transpose M C2 is 0. Orthogonality with respect to the metric supplied by M. So if we just dot this with C1, we get dot this equation here with C1. We get C1 transpose x of 0 is A1 C1 transpose C1. And then the second term vanishes with the orthogonality. And then we're left with A1 is C1 transpose x of 0 over C1 transpose C1. And similarly for A2, and in exactly the same way for V, we'd have C1 transpose V is C1 transpose C1 omega B omega 1 B1, and correspondingly B1 is C1 transpose V divided by C1 omega 1 C1 transpose C. So the A's and the B's are just found using the orthogonality. It's and if you've got an unequal mass case, you can do exactly the same thing by instead of dotting with C1 transpose, you dot with C1 transpose M, and that will secure you exactly the same property. So that's the structure of the solution. So what I then did was look back through past papers, and I saw that we're probably being unduly restrictive in the examples that I've been looking at, and the examiners have explored more complicated examples from time to time, and sometimes they produce examples which can be solved with exactly the same technique but don't go in exactly the same way, essentially because the matrices have an unexpected form. And one example that's come up at least twice in the last, well, since this paper existed, which is about 15 years, I think it was in 2003 and 2013, if I remember rightly, was the double pendulum. I don't know whether any of you have come across these questions. So if we have massless string of length L and another massless string. Now you can make this more or less complicated by making L1 and L and the two L's different and the two M's different. But it's actually quite bad enough as it stands, so I'm not going to do that. I'll just look at the equations of motions for this example. Now these are not springs; they are strings or they're rods. So what this does is it. Where's my coloured chalk? It rotates. So we can either introduce a horizontal coordinate x1 there and a horizontal coordinate x2 there, or we can introduce an angular coordinate θ1 there and θ2 there. Now, as you know, with a pendulum, you have to make some gross approximation to make the problem linear at some point, because fundamentally it isn't linear, because the restoring force isn't linear in the angle, it goes as the sine. So just treating the motion as though it were horizontal and neglecting the fact that it's going around in an arc is one way of doing that. And that gives equations of, and then you can look very directly at forces and so on. Or you can look at angular motion and look at torques about the pivot point. That's fine for a simple pendulum. For the double pendulum, it's a bit more complicated because this, it's probably easier to think of these as rigid, very lightweight, rigid rods, plastic, polythene, that kind of thing. Negligible mass compared with the masses. So this is pivoting about a point that's accelerating, and that makes it a little bit more complicated. So it's probably easier to think about in the x1, x2 coordinate basis. So I'll figure out what the equations are in that coordinate basis. And in order to do that, I need to know what the tension in the strings are. Well, certainly when it's at rest, the tension here is 2 mg, because it's got to support both the masses, and the tension here is mg, because it's only got to support one mass. And so this mass is then in equilibrium because it's got an up force of 2 mg and a down force of mg plus the gravitational force. The tension will vary with theta, but we have to ignore that variation in order to get linear equations. At least one of the questions asked you to work out the equations of motion properly and then make the linear approximation. I'm certainly not going to do that on the board. It took me an awfully long time to do it in my office, and I then ended up writing pages and pages of stuff, looking at different ways of doing it to see if there was a relatively quick way, and I came to the conclusion that I didn't think there was. So I'm just going to look at this as linear motion. Okay. So if we're looking at this motion as being horizontal, then the only forces acting are from the tensions in the two rods, and so we have M. Actually, is it probably easier if I do this in white? Is it M x1 double dot is well, there's a backwards force from this mass here, that's mg, and the relevant component is x over L, so that's minus mg x1 over L. And then there's a forwards force due to this tension, and but the relevant component is x2 minus x1 over L, so that's plus mg over L x2 minus x1, which simplifies to minus 2 mg over L x1 plus mg over L x2. And then for the other mass, we just have a backwards force due to the horizontal component of the tension in this rod, which is mx2 double dot is minus mg over L x2 minus x1. And because the forces are gravitational and all the masses are the same, the mass actually cancels through everywhere. So the equal mass case is particularly straightforward. So we have x double dot equals minus so we have 2g over L minus g over L minus g over L g over L. So that's a fairly conventional normal modes problem, actually, and in fact we've had this matrix before. It's a bit like the two masses hung on springs where the bottom mass is free and not constrained by a third spring. It's a similar kind of matrix to that. So it's symmetric, as you'd expect, but that component doesn't equal that component, and so you get a solution. You get the eigenvalues involving a non-trivial square root. There isn't a simple. The eigenvectors are not simple. However, both the questions to which I referred, one of them gave you the equations in the theta coordinates, and the other one asked you to find the equations in the theta coordinates by a rather more matrixy way. That they asked you to find an expression for the kinetic energy, to find an expression for the potential energy in terms of the angular coordinates, and then figure out what the equation of motion has to be. They're kind of tiptoeing around the edge of a Lagrangian formulation. As you very briefly met Lagrangians in the mechanics course, people nodding, good. So you know if you've got an expression for the kinetic energy in terms of the rates of change of the coordinate, and you've got an expression for the potential energy in terms of the coordinates, then you can write down the equation of motion. They actually didn't say that. They just said write down conservation of energy, differentiate it, and hence deduce what the equation of motion is. But it's much the same. You arrive at the same equation. So let's figure out what the relationship between the coordinates is. Well, x1 is simply related to theta 1, fortunately. x1 is L theta 1. But x2 is, well, what is Lx2? x2 is this displacement, which is L theta 1, plus this displacement, which is L theta 2. It's L theta 1 plus theta 2. Let's see what those two equations that I've just written down are equivalent to in this basis. It's theta 1, so x1 double dot is L theta 1 double dot plus L theta 2 double dot is minus 2g over L x1 is theta 1 plus theta 2 plus g over L. Well, that's rubbish. Well, everything I've written is rubbish. Everything I've written is rubbish. That's all wrong. So x1 is L theta 1. So L theta 1 double dot is minus 2g over L theta 1 plus g over L theta 2. Is that right? Because, where's my equation? 2g over L minus g over L x2, and x2 is theta 1 plus theta 2. And then the other equation is L theta 1 double dot plus theta 2 double dot equals minus G over L theta 1 plus G over L theta 2 plus theta 1. Probably not. No, wait a minute. It was L over G to start with. Wait a minute. What? Sorry? Yeah, there should be. Sorry. All right. There's an L there, isn't there? Yes. Which cancels the L's. Thank you. Now, you can do several different things. This is not again, these are not the equations in the form they gave you. But the point that I wish to make is that the equations that they'd given you were had the interesting matrix on this side and a diagonal matrix on this side. So let's just tidy up these equations a little bit. x1, so theta 1 double dot is minus I'm sorry? Like the first line of the diagram, shouldn't the first tension be twice as much? Yeah, I would have thought so. How long's that been going on for? Oh, yeah, oh God, yes. 2. Well, this is why they shouldn't be setting it, it's horrible. And where does that appear? That only appears, no, it's not even, yes, that's right. So here it's a 3. It doesn't appear in that one. So that's a 3. So here it's a 3. Right. So theta 1 double dot is minus 2g over L theta 1 plus G over L theta 2, and theta 1 double dot plus theta 2 double dot equals G over L. Theta 2. And you can do various things at this point. You can tidy that up to make this side simple, so you have a theta 1 and a theta 2, and that will give you the equation of the motion given in the question. Or you can tidy up the equations to make this side simple, and that will give the equation of motion in the form in which we'd already been looking at them, but with a different matrix on the left. So the point of this kind of example is that although the equation might present itself in this form, your expectation that this is complicated and this is simple may not be right in every case. And in fact, it's obvious, given that a formulation, if you change variables, you do a linear change of variables, so you write, for example, x equals L x primed, where L is some linear transformation that gives you a new set of variables, which is the kind of thing that I did over there, then that matrix L appears here, and it appears here, and then you can pre-multiply, for example, by L transpose, and you get you'll get a different matrix here and a different matrix here, related by, for example, L transpose ML and L transpose KL. So you can once you've got the thing in a matrix formulation, you can transform what the matrices are by doing linear transformations. And so you can move the complexity from one place to another. And that's essentially what's happened in this double pendulum solution. The way we derived the equations of motion, the physical interpretation of the equation that I wrote down was mass times the rate of acceleration of linear coordinate equals force. And a very simple physical interpretation. If you do a linear transformation of that, so you have some coefficient times linear acceleration of the first one times different coefficient times the linear acceleration of the second mass, that doesn't have a simple physical interpretation unless the coefficients are equal and it's something to do with the centre of mass or something. But in general, you're trading physical interpretation for some kind of mathematical transformation, which may or may not be a good thing. And the Lagrangian equations of motion are very prone to do that. They serve up the equations of motion in a form in which you wouldn't necessarily have written them down because they don't have an obvious physical interpretation in terms of force and acceleration, or at least not always. So that's one way in which the kinds of things that we've been doing are somewhat don't necessarily prepare you for what the examiners had in mind. The second way is our restriction to two variables. I was a little bit surprised going through with some undergraduates last year a past paper from, it must therefore have been 2017 probably, or possibly 2016. There was a 3-mass problem. So let's have a quick look at that. It was essentially the usual horizontal formulation with a spring and a mass, and a spring and a mass, and a spring and a mass. So let's make the masses a different colour. So there's a mass here, there's a mass here, and there's a mass here. And the middle mass had mass big M, and that was mass little m. And the springs were all equal, K, 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 K. And we've analysed that kind of problem quite a lot. I think we can immediately write down the equations of motion, which are m 0, 0, 0, m 0, 0, 0, little m x double dot equals minus. And here we'll have 2k minus k 0 minus k 2k k minus k 0 minus k 2k x. And so that's a perfectly standard form, but we're just going to have to find the eigenvalues of that 3×3 matrix. And in general, the eigenvalues and eigenvectors of a 3×3 matrix are a lot more work than for a 2×2, because if you play your cards wrong, you're presented with a cubic that you can't see the roots of. And so the trick here is not to play your cards wrong. So let me just show you that there is an important symmetry here, which is essentially related to this system here has a reflection symmetry about the middle, because these two springs are the same as those two springs, and that mass is the same as that mass. And that's reflected in this matrix, where we've got the 1 and the 3 components here are the same, and the 1, 1 and the 3, 3 components here are the same. And that simplifies the form of the polynomial which you get out of the diagonalization process. So if we just write down the matrix we're trying to solve, it's K, C is lambda m c, and that will require the determinant of k minus lambda m equals 0. And that gives us 2k minus little m lambda minus k 0 minus k 2k minus capital M lambda minus k 0 minus k 2k minus little m lambda is naught. And this particular structure that we have will mean that this is a factor in that polynomial. Let me show you. I'll expand that determinant by the top row, which gives me 2k minus m lambda times this 2 by 2 determinant here, which is 2k minus capital M lambda, 2k minus little m lambda plus k squared. And then we'll have minus k squared, thank you. And then we have minus k, which is plus k, times that determinant, which also has this as a factor, 2k minus m lambda minus k. Yeah, I think that's right. And you'll observe, and if you rush into multiplying it out, you might miss this, but 2k minus m lambda is a common factor here, and is therefore one of the, so we have 2k minus m lambda, and then we have our quadratic, which is 2k minus little m lambda, 2k minus capital M lambda, and we have minus k squared minus 2k squared, and that equals naught. And so one of the roots of the polynomial is lambda equals 2k over m. So that's relatively straightforward, but the symmetry is a bit more than that, because the symmetry extends to the eigenvectors. So let's just figure out what the eigenvector is for that particular eigenvalue. Okay? So if we put that back into the matrix equation, we get 0 minus k 0. So lambda is 2k over m, so that's 2k minus 2k. So m is m over n. Okay. 0 minus k 0. Alpha, beta, gamma equals naught, and we immediately see that k beta has to be 0, so beta is 0, and here, although I put some effort into calculating this, in fact it doesn't contribute because it multiplies beta, and we get minus k alpha minus k gamma is naught, so the other one is alpha equals gamma, and so the eigenvector is actually 1, 0, minus 1. It's the antisymmetric oscillation where the middle mass doesn't move. And if the middle mass doesn't move, then all of these off-diagonal terms here don't contribute, and we just get this equation here just reads 0 equals 0. This equation here reads x1 double dot minus 2k x1 equals minus 2k x1, and this equation reads x3 double dot minus 2k x3. So we get just simple harmonic motion on the two ends, but in antiphase. And the other two eigenvectors must be symmetric. So they will, the eigenvectors have this reflection symmetry. They're either going to turn into negative themselves under the reflection symmetry, which is this one. If you interchange x1 and x3, which is reflecting about the middle of the system, you get a minus 1, 1, which is a minus sign. The other ones, they'll be symmetric. They'll have the form A, B, A. And you just have to figure out what the coefficients are, which does involve solving that rather unpleasant little quadratic, which I'm probably not going to do, because I want to go on and say a little bit about energy, because that's the only other complication that you could possibly introduce. So, it is best to have an expectation about what you're going to get, but it's probably better to go back to first principles to think about what the kinetic energy and the potential energy are going to be. In the examples which we've looked at, the kinetic energy was x dot transpose mx dot and the potential energy was a half x transpose kx. And if you look back at how I actually derived those, I mean, this is obviously, if this is a diagonal matrix, this is just a simple sum of a half mv squared for all the masses. And so that is the correct form for the interpretation, provided the coordinate represents some linear motion. If the coordinate represents something else, then you could easily get more complicated structure here. The potential energy is one of the ways I derived this in quite a number of different ways, but one of the ways in which I derived it was to take the force and dot it with the motion and integrate, and I got this. So the energy is the integral of f dot dx, and again that's appropriate as long as that we've got linear coordinates. In fact, this is slightly more general than that, but for that to be an energy, x does have to be a length coordinate for that expression to be valid, and this has to have dimensions of force, or else torque and angle. I mean, there have to be some pair of variables that multiply together to give an energy. And then the total energy E is then a half x dot m x dot plus x k x transpose k x, and And that splits up into an energy of each of the normal modes because of the properties, because of the orthogonality properties of the vectors. You essentially get m omega squared times an amplitude squared, a half m omega squared times an amplitude squared for each of the normal modes. However, if we just return briefly and finally to that double pendulum example, so this was the 2013 question in particular. I have to exaggerate the angles to make it clear, but this is definitely, I am still making a small angles approximation here. So this is theta 1 and that's theta 2. So what that 2013 question asked you to do was to calculate the potential energy. So let's arrive at that configuration in two stages. Let's first just rotate the top mass and let the second mass hang vertically. There's no difficulty here in giving the two masses different, making the two masses different masses, M1 and M2. Then what we've done is that we have raised both masses by the same amount, namely 1 minus cos L1 minus cos theta. I'll keep the L's the same. So the potential energy is L M1 plus M2 1 minus cos theta, and in the small angles approximation that is times the acceleration due to gravity. So that's G L M1 plus M2 theta 1 squared over 2. And then we rotate we keep this mass fixed, and then we rotate this mass by theta 2, and that's increased its potential energy by a half G L M2 1 minus cos theta 2, which will be approximately another factor of a half G L M2 theta 2 squared. And then you are instructed to write this as a quadratic form. So bearing in mind that matrices are also on this paper, they can do this kind of matrixy stuff, thinking that they're drawing on the matrix side of the course rather than the normal mode side of the course. So this was a kind of hybrid between a matrix question and a normal modes question. So what you'd have would be theta 1, theta 2. You'd have an external factor of a half GL. And then you'd have the matrix, and then you'd have a theta 1 and a theta 2. And what would you need in that matrix? You'd need M1 plus M2, 0, 0, M2. And that's quite interesting because the potential energy matrix is diagonal. So, does that mean that the double pendulum is easy? Well, no, it doesn't, because when you do the same for the kinetic energy, it's a tiddly bit more difficult. Let's go back to my diagram. How do we work out the kinetic energy? The kinetic energy of this mass, the position of this mass does not depend on theta 2. The position of this mass only depends on theta 1. So if we consider a rate of change of this coordinate, it has a velocity, which I'll draw in orange. It's got a velocity there, which is L theta 1 dot. So one component of the kinetic energy is a half m L theta 1 dot, both squared, L squared theta 1 dot squared. What's the velocity of this mass? The support point for this mass is moving with this velocity, and in addition it has a velocity L theta 2 dot relative to this point. And so the velocity of this mass is the vectorial sum of those two. So that gives us that the kinetic energy is a half m1 L squared theta 1 dot squared. That's the kinetic energy of the first mass, plus a half m2 times the vectorial sum of those, the sum of the square of the sum of the vectorial sum of those two motions there, which is L squared theta 1 dot squared plus L squared theta 2 dot squared plus 2L theta 1 theta 2 cos theta 1 minus theta 2, the angle between those two vectors. Now, because of that cosine, you can't write that as a quadratic form. So you have to make the small angles approximation before you can do that. So the kinetic energy is approximately 1/2 L squared into theta 1 dot squared, m1 theta 1 dot squared, that's that term, and then we've got, and so the small angles approximation will be cos theta 1 minus cos theta 2 equals 1. If we went to the next order of approximation, we'd have a thing quadratic in theta, but we've already got stuff quadratic in theta dot, so we don't want that. These are dots, by the way, in case you can't see them. M2, so in that case we'll have theta 1 dot squared plus theta 2 dot squared plus 2 theta 1 dot theta 2 dot m2, and the L squared's gone there, so it's theta 1 plus theta 2 dot squared. And now we can write that as a quadratic form, 1/2 L squared theta 1 dot theta 2 dot theta 1 dot theta 2 dot, and what we need to put in here is an m1 and then an m2 there. So with this way of doing it, with these coordinates, we have a matrix formulation where we've got structure in the M matrix. If you then work through to the equation of motion, we end up with the usual equation of motion. M theta double dot is minus k theta, but where this is the K matrix and is diagonal, and this is the M matrix and is complicated, but it doesn't affect the solution in the slightest. It just works through in exactly the same way. We just form the determinant as we did. Where did we solve a determinant? Here. So we just form this determinant, but the structure would be in terms of the stuff in front of the m's rather than the other side. But it doesn't change the analysis in the slightest, and it doesn't change the orthogonality properties of the vectors in the slightest. So although in my view prelims ought to be a very straightforward pass-fail examination, a test of competence with an absurdly low pass mark of 40, the examiners have a way of finding new twists, which is kind of, in my view, it's that they ought not to do that, but they do tend to. So don't be phased, just think how the stuff that you've been taught applies to this situation in some way or other, and just do something that looks sensible. The other piece of good advice I would offer you is, you know, the structure of the paper has a section A and a section B with 40 marks on question A. Interestingly, that's the same number, 40. Section A is intended to be a test of knowledge rather than understanding, so do not waste time in section A trying to derive things. If you decided at the outset you were going to quote everything you needed to know to answer section A, you might occasionally lose the odd mark where it said show rather than write down, but you certainly wouldn't lose any time, which it may end up being more important to you. So do not waste time in section A trying to prove things. You've learned an awful lot this year. You can't encapsulate all that on the paper, so you just have to, the examiner is going to assume you know it if you give evidence that you do know it, and so it's a kind of bluff. The less you write down, the more you're bluffing, essentially. So bear that in mind. So tomorrow I will say some wise words about waves and dispersion. Thank you. By the way, the energy in waves handout is now complete and on the website. Should you not have noticed that, it has a complete final section. Thank you very much.
Hello.